Dit is al 175 jaar de vereniging voor en door ingenieurs. KIVI is een organisatie die zich inzet voor de belangen van ingenieurs en technisch professionals in Nederland. Kijk verder op kivi.nl wat wij als vereniging allemaal organiseren, of beter wordt lid van de grootste ingenieursvereniging van Nederland. Dan blijft u op de hoogte van de laatste technologische ontwikkelingen over bijvoorbeeld de energietransitie. En u kunt gratis deelnemen aan onze lunchwebinars, naast allerlei andere activiteiten. Hierbij wil ik u in het bijzonder wijzen op de mogelijkheden voor een bedrijfslidmaatschap. Zonder leden hebben wij geen bestaansrecht. Our speaker for today is Tobias Luke. Since 2016, Tobias Luke is an accomplished professional embarked on an academic journey at the University of Paderborn, earning a master's degree in electrical engineering. From 2016 to 2017, Tobias served as a research assistant at the university, specializing in sensor technology. Sorry. Subsequently, Tobias contributed to the Fraunhofer Institute for Electronic Nanosystems, INAS, in Paderborn from 2017 to 2018. Transitioning into industry, Tobias assumed the role of product manager at Phoenix Contact BU Power Supplies, specializing in DC-DC power solutions from 2018 to 2023. Since 2023, Tobias has excelled as a technical project leader at Phoenix Contact BU Power Supplies. Tobias will take you the next 40 minutes into the world of the direct current, and the possibilities for the energy transition, special in case with the problem of net congestions. I wish everybody an interesting presentation, and Tobias, the floor is yours.
Yes, hello and welcome from my side, and thanks for this nice introduction of my person. First of all, thanks to KIVI for letting me talk about DC industry and DC grids industry. I will share my screen, and also many thanks for everybody that is attending today. So the topic for today is DC grids and industry, and since the introduction of my person was already started, I will skip that. I'm coming directly to some facts and figures of Phoenix Contact as a company. So Phoenix Contact was founded in 1923 in Essen in Germany, and after World War II we moved to beautiful Blomberg, where our headquarters is. We have more than 22,000 people working for Phoenix Contact in over 50 countries, and I think that the most of you already had one or two products in hand of Phoenix Contact. We have more than 100,000 products for basically all kind of industrial applications available. And Phoenix always standard for innovative products, innovations. And this is also the reason why Phoenix also is part and contributes in the all-electric society. And I would explain what the all-electric society basically is. And the all-electric society basically describes a world where the renewables are the primary energy source. And in order to achieve that, the coupling of the relevant sectors, energy, industry, infrastructure, and mobility.
Ik heb u toch nog even gesproken.
Sorry, we hear you. Could you mute your phone? Thanks. Is one key component, and on the other end, optimizing the whole energy chain by means of energy generation, energy distribution, storage, and consumption needs also to be done. What does it mean in practice? So sector coupling is the main driver. That means power generation, distribution, storage, and consumption need to be integrated into one holistic system. We need to achieve optimal flow control by analyzing the data, and all the data are gathered with an enhanced and overall efficiency communication protocol. And DC technology, as we think, is a key technology on the way to the all-electric society. And now I want to explain why DC gets more important and popular over the last years, and also why we're currently dealing more or less only with AC. In order to answer the second question, we need to step back a little bit in time. We are in the late 1800s when the War of Corinth was occurring. So basically, George Westinghouse was fighting against Thomas Edison. And the question was, what would be the standard for power supply worldwide? Is it AC or is it DC? And at the end, George Westinghouse got the go to power the World Expo. And this is basically the time when the success of AC started. And it was decided because back in the days, transforming energy from a lower level to a higher level and then distribute that over long distances could be easily achieved by using a transformer. And a transformer could be easily built. You only need iron, isolation, and copper, and then you're basically ready to go. The disadvantages of a transformer of this principle is it only works with alternating current. Due to the last developments in the last decades, in terms of power supply, power modules, integrated circuits, the new standard of transforming energy are switch mode power supplies, power electronics. So you can easily transform DC to DC, AC to DC, or DC to AC. These devices are more efficient, they are cheaper, of course, smaller, and they are now the new standard. So with respect of transforming energy, a new development was done, and same is also occurring now with DC technology and DC grids, which brings me now to the motivation for DC grids. The first motivation is sustainability. So integrating renewable energy sources reduces the need of an AC to DC conversion, and therefore we save energy. The second one is energy efficiency. Within a DC grid, recuperation, kinetic energy can be easily fed back to this DC grid, and it can be supplied to other DC consumers. Load peaks are reduced with these recuperation and renewable energy effects. This will save costs significantly. By building up a DC grid, you will use less resources. So basically less copper, smaller components because you get rid of the AC component within a converter, and you need less converters. And if you combine all the advantages of a DC grid with an intelligent management, you will definitely decrease the dependency on the public AC grid, and you will have a much more stable grid in terms of a DC grid. All right, now let's talk about the different areas, and I want to start with DC transmission. And here I want to show that DC transmission is state of the art. This map here shows the DC transmission line, mainly over sea, that are already installed and existing in Europe. And even in Germany, there is a DC transmission line under discussion, which is planned from the northern to the southern part, which is called SüdLink, to transform or transmit the wind energy to the southern part from the northern part. And the DC transmission basically is done between 100 to 1000 kilovolt DC. The second one is the generation. For example, let's take PV. So a PV panel produces DC in order to be efficient. Most PV parks use MPPT trackers. So they have a DC intermediate circuit, and this DC voltage is inverted then to AC again. On the other hand, even wind farms are working on DC intermediate circuits, and fuel cells also working on DC voltage. So in the power generation, DC is also a topic. The conversion we already talked about. On the right-hand side, you see a classical switch mode power supply. As I said, they are much more efficient. And switch mode power supply and DC-DC converters in general work also on DC internally. Now we are coming to the consumers. So basically, everybody is using a laptop, or at least looking in a monitor or using a smartphone. All these electronic consumers work internally on DC. The lighting we have work on DC. So that means DC in the consumer world is set. Heat generators, they don't care if they get AC or DC. Industrial inverters, as shown on the picture, normally have an AC input, have a DC intermediate circuit, and then an AC output to power up a motor. And in general, the demand of three-phase current devices is constantly decreasing. So also on the consumer side, most of the consumers already work or can work on DC. Now we are coming to the storage. Here's the example of a battery energy storage. And in order to really close this slide, is battery energy storage is run all on DC. So there's no AC part in a battery energy storage, and it's much more efficient to connect the power conversion system of a battery energy storage to a DC grid. I want to close the advantages by an example why a DC grid is better than an AC grid. On the right-hand side, you see a graph of the effective current per phase of a non-continuous drive. For example, it is a robot which is lifting a heavy load, and for each lifting a heavy load, you see these current peaks. And the electrical system must be designed for the maximum of the current peak, and this will cause a lot of costs. Even if these current peaks only occur several times, and is not a constant current. If you compare that to a DC grid, and the DC grid is allowing to feedback the potential energy by lowering this load again into the DC grid and make it available for other loads that are lifting a load, you will basically have the acceleration power and the braking power, which will lead to a load balancing. So that means that the overall effect on the upstream grid is less, the grid design is smaller, and the use of recuperation energy was basically the main motivation for the research project DC industry. Coming from the advantages, I want to talk a little bit about the fields of application in general. And by talking about the fields of application in general, we are back to our sectors, which are energy generation, energy storage, the distribution, and the consumption again. And it doesn't matter in general if a battery storage is running on 1000-volt DC or a solar plant is running on 1500-volt DC, a factory automation is running on 650 or 800-volt DC, or a data center is running on 400-volt DC. All these sub-applications could benefit from the DC technology by itself. Nevertheless, what the voltage is. Even railway, the German Bundesbahn is thinking about a digital rail, which also could work on DC in the future. Charging parks, DC charging for electrical vehicles is well established. And the idea of an industrial grid is firstly shown here. And what you see, it really combines all the sectors. You have the energy sources, you have the energy storage, you have the consumers, and you have also the transmission or the connection to the public grid. And this is basically the idea. And of course, you still have the connection to the public grid. And a so-called active infill converter is then building the DC grid. It's building the backbone. And the bidirectional power supply basically is doing it. And the DC backbone is kind of the heart of the whole DC infrastructure. And all other devices like an energy storage, if it's running, let's say, on another voltage, then the DC backbone could be connected to this DC grid by use of a suitable grid interface, maybe a DC-DC converter. And from this idea, we also derived the idea that an intelligent grid management is mandatory in order to have really a stable grid. And basically, what we have seen that high power modules basically build up the DC grid, Control technology intelligently controls the power parameters with respect to the high power modules. And this basically forms the the basis for the DC grid management. And if you combine all these sectors very intelligently with each other, then you have an overall intelligent grid management, which makes you less dependent from the upstream AC. So far, so good. So now we want to come from theory into practice. And that means I want to show you another example of a DC grid, which is a new building that Koninklijk is building. It's the building called G60 at our headquarters in Blomberg, which will be the new home for the machine building of Koninklijk. And this building 60 is the blueprint for smart and sustainable sector coupling. As you know, the sectors industry, energy, infrastructure, and mobility. And before we started building this building, we kind of based this building onto 3 columns, which are the basics, the thermal energy concept, and of course, the electrical energy concept. The basis was we wanted to have a CO2 neutral building. And the building needed to be built to the highest efficiency standards that are currently valid. And we wanted to achieve the cradle-to-cradle approach. That means all the materials that are used within this building should be recyclable. The thermal energy concept is very special because we are combining an ice storage to a heat pump, which makes the heat pump very, very efficient, even in cold winter days. And we are connecting this building to our heat network of the facility, of the whole headquarters. But the main focus today will be the electrical energy column. So the main part of the building is still powered by AC, but we implemented an industrial DC grid, which is connected to a battery storage, which is connected to the PV on the roof, which is connected to bidirectional EV charging, and which will be also connected in the future. That's our idea, to power hydrogen and a fuel cell. Speaking on the PV, so here you have a picture, it's a rendering. So this is how the building will look when the construction is finished. The PV is already installed on the roof. We have 1.5 megawatt peak. We have another megawatt peak on the open field. And around 110 kilowatt peak of this 1.5 megawatt on the roof are directly connected to our industrial DC grid. So by planning such a grid, we still decided that the main facility needs to be powered by AC. And this is the reason why 1.5 or almost 1.5, 1.4 megawatt peak are directly connected to our 400 volt AC station. We are connected to a 30 kilowatt public grid, and lighting, building automation, and production is connected to our 400 volt AC. Nevertheless, our DC grid idea looks as follows. So starting with the bidirectional active infill converter, which is the backbone of our 600 volt DC bus. As I said, PV is coupled to this DC bus, also a battery storage, EV charging bidirectional, and we implemented 400 volt IT for lighting, building automation, and parts of the production. So far, so good. So far, also theory in our minds. And by building such a new infrastructure, this DC grid, we came along some challenges. And first challenge was, okay, how could we find appropriate components like power supplies, devices for arc suppression, protection against overvoltages and overcurrent, switching high voltage DC, of course, the grid and load management. We need to find somebody that is helping building it. And the solution was, first, be open-minded, work with partners, develop new products from us, and also look around with our colleagues what kind of products we already had. And by looking in products what we already had and also developing new products, this idea of building a DC grid really became into practice. And what we are seeing here is the circuit diagram. So that is basically how our DC grid is really looking like. And on the upper left, you see our active infield converters. They feed our low voltage main distribution 600 volt DC TN grid with 700 kilowatts. This is supported by 4 times 30 kilowatt DC-DC converters, which are connected to the PV. We have the battery energy storage for charging and discharging, our e-mobility charging stations, and our end circuits like lights, building automation, all the 24 volt appliances, we call them end circuits, are running on the 400 volt DC IT network. And of course, the machine directly will be connected to our 600 volt DC grid, so all the heavy loads within the machine in order to investigate the effect of recuperation. This is the current status of our DC grid. In terms of the cabinets, they are assembled and equipped. The main distribution is installed, which is in the basement, and the sub-distribution is also installed, which is on the shop floor. The PV is on the roof, and it's finished. The final checkup in terms of the cabinets is ongoing. The battery energy storage is in place and will be connected to the DC grid shortly. And the DC charging stations are also built up and also so connected to our DC infrastructure. And the question now is, why is a company like Phoenix doing this kind of implementation of an industrial DC grid? First of all, we definitely think that the all-electric society is important and that DC grids will play in the future a major role towards it. I already explained the advantages, and this really brings us closer to the all-electric society. We definitely believe that. Secondly, we really want to gain experience in DC grid planning, installation, and operation. We really want to know what we are talking about. It's not just about the product, it's about the whole solution. The idea of the grid management needs also to be tested in real life. And in our own facility, it's our playground to test that. So this is the second reason. Also, we need to test and gain practical experience with our DC components. But we are also open-minded to other brands. So if one of you have a component that should be run in a DC environment, we are very open to open the doors and let you in to test your devices as well. And of course, in terms of efficiency, we really want to investigate DC-powered production machines in terms on recuperation. Which brings me down really to the production machines, which are connected to the DC grid. And we were investigating different scenarios. And this is, I think, the most likely scenario we will implement, that we say on the machine itself, we will have no converters at all. So basically, we will have our 600 volt main distribution. And from there, we will convert 48 volt and 24 volt for low load drives. And the recuperation of all voltage levels is something we really want to investigate. And here we are seeing only a single machine on a really platform. It could look like this. Here is an example of 3 machines where we say, okay, heavy duties, 600 volt directly, and we will convert to 48 and 24 volt for low dynamic drives. And the idea is really to exchange energies between the machines and really be more efficient in terms of DC. And we open ourselves the option to add additional energy buffers to the system. If low peaks are coming, recuperation peaks are coming, to store them, for example, in supercaps, stuff like that. So it's, like I said, not well set at the moment. We are very flexible and we want to test a lot and really experience our knowledge on DC powered grids. Now I'm coming to a current situation. I already was talking about this research project, the DC Industries. Basically, this research project took place for 6 years. With Corona, let's say almost 7 years. And the ODCA, which is a foundation, was derived from that project. Most of the members of the DC industry are also the core or the founding members of the ODCA. I think we are started with around 30, and here we state it's over 50. I think we are close to 60 members from different parties, industry, research, and university. And besides the industrial applications, we really want to derive more blueprints for further applications, like, let's say, data centers, maritime applications, and so on. And the vision is clear: to support the all-electric society, to support a world that is CO2 neutral. And the mission is to really build an international DC ecosystem. So that means establish DC across a variation of applications. And the vision is clear. We want to have a close cooperation between all parties: planners, manufacturers, suppliers, research, institutional and associations, standardization agencies, and so on. And what we are doing, we are working on different topics and on technology, research, and standardization. And it's an open community, and everybody here is really welcome to contribute in the ODCA. This is something I couldn't give you. In speaking of international activities, here we see a list of activities that are ongoing. Of course, the ODCA, but we also have activities in the Netherlands. I think most of you know Current OS. There are also universities researching towards DC. We have activities in Asia, South Korea, in Japan, in China. There are activities in America, like Canada and the United States. And the big question is, are all the low voltage DC components that are available on the market suitable to be placed in all these activities, or is there a lack of research or a lack of availability in components? And if you take a closer look into these approaches of different areas, you see that there's an approach on more or less a 400 volt to 800 volt, a 600 volt approach. There are also approaches with 100 volt DC that's also beneficial and taking the advantages of DC in general. But there are also movements up to the upper level of the low voltage directive, which is 1500 volt DC. And I think it's very important to really align and combine all the activities in terms of voltage, in terms of topology, in terms of regulation and standardization in order to make this DC grid very, very successful and put all the ideas together in one pot. This is just a slide about some products of Phoenix. So we have a broad variety. I don't want to go too much into detail. And basically, we are coming now to the final question: is does DC power grids in industry solve grid congestion? To be honest, it is not very easy to answer that. And for me, there's not a clear answer. But I will definitely say DC powered grids have a positive effect on that. And first of all is because of renewable energy integration. So that means the integration of renewable energies could be much more efficient. We will have a much more efficient energy distribution and energy consumption, for example, due to the use of recuperation energy. So there are test plants where up to 10% of energy consumption could be reduced because of the kinetic energy, which could be fed back to the DC grid and could be supplied to other loads. And due to all the effects and intelligent grid management, we could by 100% reduce the dependency on a public grid, which is kind of the answer of the question above, I think. That was from my side. It's a short introduction in the world of DC with the advantages, with how to build up a DC and an example how a DC grid could look like. Also about the challenges we came along and also the international activities from my point of view. And I think now it's time for some question and answers. So if there are any questions, you are now have the chance to ask some questions.
Okay, Tobias, thank you very much for the presentation.
You're well welcome.
There are not so many questions, maybe there will be. My question is, when I hear you speaking about DC, what are we waiting for?
At the moment, I think sometimes the lack of standardization and the availability of products that are, I would say, sometimes affordable. So the technical way is always well described, but it comes down to deciders. They say, okay, what is the real benefit? What will it cost? And is it easy to use? So sometimes people are afraid. Sometimes they have thoughts about availability of products. In my opinion, we are ready to go. We are good to go. We really need to spread this idea and really get more people together to really be there.
At the other hand, what I see is that there are so many differences between the countries and parts of the world about the DC. And what the questions about what I've seen in the chat were more or less about those topics about why are there so many differences between Germany, Holland, but also China and all over the world. Sometimes is it 600 volt DC, then 700 volt DC. There's no standardization. What I understand. Why not? Why is that part of the deal that it's so difficult to get the DC going?
Correct as well. There are two questions. One is the question of the absolute voltage, and the other question is about topology. Will it be an isolated grid? Will it be a AC-sided grounded grid? And in my opinion, the reason is why there are so many voltages under discussion is it depends on the application. Let's say photovoltaics, they're running for years now on 1500 volts. Battery storage is, I think, 1000 volts is standard. They will also go up to 1500 volts. For the industry, the 650 volt, let's say this band from 400 to 800 volt was derived out of a three-phase rectified voltage. So for the industry, the 650 volt could be the most suitable one. For a energy storage could be another one. For a data center, it could be another one. The question is, will we be able to integrate these different movements from the different sub-applications into one suitable application? What could be a DC grid in industry? And I say definitely yes, it would be possible, and it is possible, and we are showing that.
Yeah, but is it not possible that the scientists all over the world come together and make one standard?
That would be nice.
Yeah, I mean, why not? I mean, I can understand that politicians are very more or less afraid to do that, but I think that scientists or technicians all over the world has the same idea what's the best to use, and maybe you can use a band width. You can say, okay, not only one but more DC currents are available or suitable, but let's make a choice of it. Let's do it 650 700 DC, full DC. I don't see very much difference, but there is a small difference. Why? And I think is it the protection of the industry, of their own industry, or what?
It's actually a good question. I try to answer it on a way from two perspectives. One perspective is the manufacturer of components, and the other perspective is the planner of application. So the planner of application, in my opinion, basically wants to have the biggest benefit out of a DC grid. So if you double the voltage, you lower the losses by factor 4. Okay. So for me, it makes totally sense to go in all applications up to 1500 volts. That's a thesis from my side. Okay. If you are on the manufacturer side, as we are, we need to look on the power electronics. What kind of power electronics are available that can handle 1500 volts? And there are only rare of them. So that could be on the component side, a lack of technology. So if that is kind of answering your question.
Okay, so what that concerns is yeah a bit a problem with many faces, many heads, and it's hard to solve this with one solution. I will go back. We have lots of questions now. I will see if I can read them about. Even kijken hoor. Oh yeah, what's the difference? Nice question. What's the disadvantage? What are the disadvantages of DC? Are there any
disadvantages?
Disadvantages of DC?
Yeah, I won't say disadvantages. I more or less say challenges. And one challenge is the arc suppression, arcing. So if you disconnect a load, under load, you don't have in an AC world your alternating current. So you don't have your neutral, which you are pathing like in a 50 hertz 100 times. So that means if you, let's say, plug disconnect a plug, and there will be an arc, this arc won't distinguish itself. So there needs to be technologies, which we are also developed anyways, that suppress arcs. There are mechanically ones, there are electrical ones, in order to really be safe in an operation. So this is like a challenge, in my opinion. But kind of this is already solved.
Okay, and a question from Steven van Zomeren. Do you think that DC is most likely to emerge on a large scale in local grids compared to the regional, national, and international grids?
I think the voltage level in the industry, for me, the idea for the 650 volt makes quite sense. If you want to really overcome long distances, okay, on the low voltage directive, you can go to 1500 volts. In my opinion, it depends on the application. So there's not a standard answer on that. I would definitely say it needs to be decided application wise. But on the let's say factory side, I think this 650 volts, let's say 400 to 800 volt is a good choice. Yeah.
Okay. Is DC the solution for heavy duty transport?
What is the meaning of heavy duty transport? Like machine handling, material handling?
Yeah, or railroads, or.
Okay. Yeah. Okay. I see where the question is. I know that trams already running for years on DC. So this is something we had for the last 50, 60, 70 years. I know that we are having e-highway where electrical trucks are running on. The German Bahn is working or driving on 16 2/3 hertz, I think. The answer from my side is that there are investigations into that by truck transportation, because if they want to run on batteries in the future, they need to be charged. It could be partly possible if it's something that would be a solution for all heavy duty transportation. This is really something I can't answer.
No, but the question is about trucks. I see this. So can run trucks on DC? Is the question.
Yeah, basically, yes. Why not? I mean, EV cars also run on DC. There's, I think, from the IEC, also a new standard under development, which describes conductive battery loading for trucks up to 1250 volts. So that could be something for trucks as well, yes.
Oké. Dit hebben we gehad. Even kijken. There is in the presentation nothing about the problem of handling short circuits. How is this done?
Okay.
Per installed megawatt of drives of SCC.
Okay.
I don't know what it is. Yeah, you understand the question?
So handling short circuits. So what we did, we built our DC grid in accordance to the DC industry system concept. So that is like the outcome of this research project, okay? And it's like kind of like a recipe how to build a DC grid. It's a very, very long document which really has examples and kind of describes everything you need to know, okay? And within the industry concept, it says that the short circuits need to come from the DC grid itself. And we developed a new device. It's called electronical load relay for high voltage DC. And it's basically an switch and DC switch, which also has like a breaker characteristic. And the specification basically is 800 volt and 55 amps, and it is there to kind of secure subsectors like this DC microgrids. So you can install it from a DC backbone to a battery storage, and the breaking characteristic you can basically define by yourself from or up to 55 amps. So that is the solution and the answer component-wise in order to trip and secure different sectors from the main distribution.
Okay. I have another question. Ernst van der Pol asked in chat, another disadvantage, the AC grid voltage amplitude is controlled via the voltage frequency. With a DC grid, the value is always 0 and it's not available as an information carrier. Do you agree with that? Or
it's right. It's right. So the main steering method on AC is the frequency, and here in Europe we really need to hold this 50 hertz. You don't have the frequency in DC. It's always 0. So that basically is not a disadvantage in my opinion. I think it's an advantage because it really easily integrates the possibility to add more DC sources to this DC grid because you don't need to synchronize it to this 50 hertz. So it's very easy, and this is why we say it's much easier to add a DC battery storage to a existing DC grid instead of having this DC battery storage inverted to AC, synchronized to the AC environment. So in my opinion, it's actually not a disadvantage to run on DC. For me, more or less, it's an advantage because it makes it much easier because you don't have to focus on the frequency and harmonize it and synchronize it.
Yeah. Even a question of Damien Zuidervliet. Will the DC grid at G60, the building, also have a nice breakdown of all the voltage levels for drop the balancing like specified in the current OS protocol?
At the moment, we are focusing on the system concept from the ODCA, respect the DC industry, which is in our building 650 volt plus minus 10%. With AC-sided grounding as a first voltage level. And the second voltage level will be a 400 volt isolated grid for lighting as an example. The current OS foundation is also working And yeah, talking to the ODCA, this is a way where we internationalize each other and try to define the standard. So that is correct, yeah.
Okay. I see that's not a question from Mr. A. Hogewerf. He says in DC power is handled via the voltage, so there is normally an UP control instead of a PF. And I really don't understand that, what is meant by that. Mr. Hogewerf, maybe you can help me. Okay. Let's see. There are questions, or not, there are no questions, but there are people who said scientists are already talk with another one of our electronic friends is Harry Stockman.
Yes.
Do you know him, or?
Yeah, I met Harry. Harry is
Michael Herlaan. Yeah, so there are some talkings behind the screens about now how to level up with each other. Is that correct?
Yeah, of course. I mean, I know Harry. I know that he's kind of the inventor of the idea in the Netherlands, I would say, more or less, kind of working on current OS and everything. Yeah, you're right. There's an exchange, and that is also necessary, I think.
Are there more of those exchanges? You know?
Last time I saw Harry it's quite a while ago. I say it's 1.5 years ago. But I'm also not the main driver towards that. This is also discussed on another level. So how frequent the discussions are, I can't say for sure. But I know there's an exchange, which is in my important, very beneficial for the overall idea and the overall approach. Yeah.
Yeah. And do you know of any other people or countries are talking to each other, with each other, about the standards?
We as Phoenix Contact try to also use our influence within the countries and talk to the people. That is what we as Phoenix as a company do.
Yeah, is Phoenix the only company who does that?
No. If you look on the ODCA side, you see many partners from industry, research, also standardization organizations, universities. Yeah, it's a broad portfolio with a lot of members.
Yeah, and what I understand is that the industry or the producing the products has to do with the electrics, and the policy of the countries to protect their industry. Is that more or less the barrier of on the developing of DC? Or introducing DC, or make DC special of DC more or less the same in all countries?
Let's say when I talk to people that don't get to know or they didn't know DC before, they are so, oh wow, what is that? It's cool. Why don't we use it right away? Basically the same kind of question you are asking.
Yeah.
It's more or less a lack of knowledge, and everybody knows AC over last 100 years. So for everybody, it's so easy to use AC, and DC is like the new stuff, the new great thing, you know? So, I mean, as it always is with new technology, they need to be established. And I think it's about knowledge establishment.
Okay. And the industry is talking to the politicians about this.
That's actually also a difficult question. I think actually what the politics is doing, at least here in Germany, they say, hey, industry, try to be more CO2 neutral. And then the industry is looking into mechanism to achieve that goal. And if we explain the industry that the DC grid could be a good vehicle, a good weapon to be more efficient, I think this is the way.
Is in your opinion, is this the only way of coping with the net congestions?
Only Europe? No, it's a global thing.
No, not Europe. I mean, is the DC the only solution to the net congestion? because
no. It's no.
Because you have to.
As I said, what's described over here, it's the all-electric society.
Yes.
And DC could be one key technology, and we definitely believe that DC is a key technology. But what the all-electric society basically describes is that renewables will be the primary energy source. So, and that means we will independent from the AC, and this could be done by really efficiently, intelligently combine the relevant sectors, the different sectors of, let's say, the production, the charging, the generation, the storage, all of that. Also with prediction of consumption, prediction of producing, this, all of this could be help to be more independent from the AC grid. Also get to know what kind of usage is going to be needed in an hour. How is the sun shining at that time? So all the combination, we need to be more intelligent with our grids. And this is kind of helping towards that. And a real benefit, direct benefit, and a real driver for the all-electric society, I think DC grids are that.
Yeah. Do you think that DC is more flexible than AC/DC?
In terms of what do you mean?
Then you can, when the sun shines, you have more electricity, and you can use it or not, and you have to cope with what are I going to do with it? Do I store it or do I use it? Or what's the price? Is there DC a better format?
Your first question was more flexible.
Yeah.
I wouldn't say directly yes or no. I would more or less say it's more efficient.
More efficient.
And it's maybe easier to be handled. Okay. But all the things you can do, I mean, take your home, you have your PV on the roof. I mean, it's working fine, and at your home you have AC. So you can handle it, but the benefits a little bit lower, I would say.
Oh, okay. And this is not a question, but a remark. He says the Hogewerf power control in systems in DC is done by the voltage instead of by frequency. That's correct? Okay.
Correct. And that is what we achieve with the grid management, basically. So we really want to control each high power module for each sector by voltage in order to, kind of control the sectors on the DC bus itself.
Yeah. Okay. A question of Steven van Zomeren. He says, when do you expect that DC grids will become standard at home?
Oh, okay, yeah. I would love to answer the question, to be honest, 100%. Moreover, I would also love to answer the question when it will be a standard for the industry. Instead of answering the question, I would give everybody on the way here, believe here, try to really spread the idea of DC and help to make DC very successful for the industry and also for residential applications.
I think that's a good remark from you to all our viewers. There are a reasonable amount of viewers, and I hope that everybody can do something about the knowledge of DC and the advantages of DC. And because in the all electric world, we need to be more efficient and to do things otherwise than we've done before, and I hope this webinar will contribute to it. Thank you very much, Tobias.
Sure. It was a pleasure.
Yeah, we have done all, I think, more or less all the questions, though, so we don't have to send you the questions and for the answers, and we don't have to distribute them to all the attendees. Thank you very much again for your interesting presentation. You will receive shortly a gift of appreciation.
Thank you.
Please hang on because we have to talk later on. But now I want to finish and I want to end our webinar in Dutch. So
maybe one last comment from my side,
yeah?
if I'm allowed to.
Please.
For all the audience here, first of all, very thanks that you really got in touch with this interesting topic. If there are questions afterwards, okay?
Yeah.
Don't hesitate to contact me or one of my colleagues. We are really happy to really get you more insight about the DC world with Phoenix, okay? Very, very, very honest offer from our side.
Okay, thank you very much. I will put that in Dutch and I will ask them to put those questions via the KIVI so that we can provide all the answers to everybody who has attended this webinar.
Thank you.
Okay, and then I go on. Oké, even zien hoor. Het webinar is opgenomen en later beschikbaar op het KIVI YouTube kanaal, wat bekend wordt gemaakt op de website van KIVI. Het volgende e-lunch webinar is op woensdag 20 maart en het is nog niet duidelijk welk onderwerp er zal worden behandeld met betrekking tot de energietransitie. Maar kijk vooral voor deelname op onze site kivi.nl en houd onze KIVI LinkedIn pagina in de gaten. U bent wel tijdig op de hoogte. Namens KIVI wil ik iedereen bedanken voor de belangstelling. Wij zien u graag terug bij het volgende e-lunch webinar of een andere activiteit. En nogmaals, wat Tobias voorstelde en ons aanbood. Als er nog vragen zijn met betrekking tot de DC, stel ze gerust via de KIVI. Wij sluizen dat door naar Tobias. En dan zorgen we ervoor dat iedereen ook alle antwoorden te zien krijgt. Dat is denk ik goed voor de verspreiding van de kennis. Voor nu wensen we u nog een fijne dag verder. En ik zou zeggen tot ziens.